Hello folks, welcome to this channel. I'm Saptarshi Mukherjee. I'm a software engineer 3 at Google and I'm a competitive programmer. So in this video, I'm back with another problem, another DP problem from the CSES problem set, coin combinations 1. This is the third problem of DP in this playlist. So let's look at this problem. It's slightly similar to the previous problems that we have discussed. The problem says that there is a money system with n coins and each coin has some positive integer value. It's like a denomination. And using those coins, what is the number of distinct ways to produce a money sum x using the available coins? So basically, some coins are given 2, 3, 5 and using that we have to produce 9. So these are the coin types, and each particular type of coin we have many different coins for that. Like of value 2 we have infinite coins of value 2, we have infinite coins of value 3 and so on for 5 as well. And then we have to prepare this sum. So how many ways are there to prepare that? That's the question. So essentially we have some n types of coins, each coin present in infinite number, and their values are given in an array, and we have to count the number of ways to produce a certain sum using those coins. So this particular example 2, 3, 5, to produce a sum of 9, let us see. Using 2, 3, 5, this is one possibility. We take the coin of value 2 3 times and the coin of value 3 one time. This is one way, 2 plus 2 plus 2 plus 3. Now the ordering, if the ordering changes, that becomes another way, like 2, 3, 2, 2. It's given in the question. So sometimes from the example that is given, you have to identify whether the ordering matters or not. So over here, the ordering matters. They get counted as two different ways. So essentially, 2, 2, 2, 3, 2, 2, 3, 2, 2, 3, 2, 2, 3, 2, 2, 2 are all different orderings, different ways. 2, 2, 5, 2, 5, 2, 5, 2, 2, 3, 3, 3, these are all again different ways. So in total we have 8 ways possible using these coins, and that is what you need to find, that you have a certain sum, you have to reach a certain target, and you are given some elements in an array. In how many ways can you reach it? Now we have covered a similar problem, so let us first look at that. In another video we had covered a similar problem, which was dice combinations. We had to reach a sum of n by throwing a dice one or more times, and each time it comes with a different outcome. Each time the outcome was between 1 and 6. So we basically said the same thing, that how many ways are there to reach a certain sum, let's say 3, and we saw that okay, we have these 4 ways. 1 plus 2, 2 plus 1 we had counted differently. So over there in that question we basically had, let's throw some dice, the outcome 1, then outcome 2, then outcome 3. Their summations, basically whatever number of outcomes we are taking, that has to be equal to the sum, that is x. Similar over here. And over here our outcomes are not from 1 to 6. Each particular element will not be from 1 to 6. Rather they have to belong to a certain array that is given to us. So the elements have changed, our choices have changed, but the other part of the question, the substance of the question, has remained the same. Let's look at the constraints. The constraints are n goes up to 100, that is the length of the array, and the total sum goes up to 10 to the power 6. Now, how did we solve this problem? This is a classic number of ways problem, which we had solved in the dice combinations problem. If you did not watch that video, please go back and watch that video. And if you did not watch the the common video I made on DP, that is the first video of the playlist, please do go and watch. There I have discussed the basics of DP, how we approach DP problems, the basic structures of DP, like overlapping subproblems and optimal substructure, and then how do we decide between tabulation and memoization. You will find it helpful to follow this video using those videos. But anyway, for number of ways kind of problems, we basically say, okay, you have to reach x, very good. So focus on this x. In how many ways can you reach? Let's focus on the last coin that you will take. The last coin. You have only 3 options, 2, 3 and 5. If you think about all the steps that you take, that will become clumsy. So think about one step at a time. The last step can be either 2, 3 or 5. So think about that. That okay, let's say these are your three options, 2, 3, 5. In that case, you basically want to know how many ways can you reach x minus 2? How many ways can you reach x minus 3? How many ways can you reach x minus 5? And you're basically saying, hey, in what you're taking, how you're forming x minus 2, I don't care. I'll count each of them as a way. So whether I'm taking 2 or 3 or 5 doesn't matter, doesn't influence how I'm going to form this sum, which means form those sum in their way. X minus 2, let's say, you can form in C1 ways. X minus 3 you can form in C2 ways. X minus 5 you can form in C3 ways. Then you can form X in how many ways? C1 plus C2 plus C3. This is the common strategy we use for these number of ways kind of a problem. We say that these are the possible options for your last step or for your first step. So decide those things. If you decide 2 as the last step, you have C1 options. If you have 3 as the last step, you have C2 options. If you have 5 as the last step, you have C3 options. And they are all independent. So the final answer will be the sum of all these options. This is the classic number of ways problem solution approach. So let us see how we should apply this. So basically, if we have 8 at hand, then the recursion way of applying it basically would be that we start with 8 and then we say, hey, there are 2, 3, 5, these options, 2, 3, 5. So if I go with 2, that means the remaining part is 6. So this 6, I have to find number of ways. For that, again, I'll do the same thing. 2, 3, 5 are my three options. 2, 3, 5 are my three options. So I basically get 4, 3, and 1 to be solved. And for 4, again, I have three options. In fact, 5 is not an option for 4. So I only have two options, 2 and 3. Now, 1, basically for 1, we have no options. So 1 is not a possibility because 1 cannot be formed. For 3, I have two options, but again, this 1 is hopeless. This 0 gives me a hope, okay. This means this is one path. If I take 3, this 3, and then this 3, and then this 2, this is one path. This is one path, this is one way I can count. So eventually, we can basically complete this process. This one has no hope. We have 5. So basically, we can go back from here. We can say this 2 has only one option, 0. So this 0 gives us one way. There is one way to reach 0, that is do nothing. We will send back this 1, and then 2 also can be obtained in one way. That is by subtracting this 2, by basically taking the 2 coin. And then we'll go back. We will basically take it back. And 1, this is not possible. So we have only that one way up to here. For 4 also, we have only one way. In this way, the recursion problem can be solved. Over here as well, we have only one way from here. So 1 plus 1 at 6, it becomes 2 ways. 6 can be formed in 2 ways. 3 plus 3 and 2 plus 2 plus 2. How to see that? 2 plus 2 plus 2, that is 6, and 3 plus 3, that is 6. What else? Now we have 5. For 5 again, the same process starts, but this time, the moment I say 3, I can basically say, okay, I don't need to go further down. This is memoization. This is overlapping subproblems. This 3 matches with this 3. So I know that for 3 the answer is 1. So I will directly pass 1 back. And there is another way. If I take 3 directly, then I'll remain with 2. And for 2 also I know the answer. I'll send that back. For 2 the answer is 1. So for 5 also the answer is 2. Now if I subtract 5 from 8, I remain with 3. And for 3 I know the answer. The answer is 1. So I'll pass back 1 from there. And hence I get to 2 plus 2 plus 1. That is there some issue? Sorry, for 3 the answer is yes, for 3 the answer is 1. For 5 the answer is 2. For 6 the answer is 2. So the answer should be 5, but the answer is not 5. The answer, okay, I solved for 8. I'm sorry. I had to solve for 9. For 8 the answer comes out to be 5. For 9 possibly we'll get a bigger answer, yeah. So this is for 8. Now, this is a memoization way of solving the problem. That is, I start from the main target, the main answer, and I go towards the smaller cases. This is known as top to bottom approach, top down approach. And the way of using the already computed solutions like 3 and 5, uh, like 3 and 2, without recomputing them, that we refer as memoization. Yeah. So basically, the inference is if we know dp of 6, dp of 5, dp of 3, that is the answer for these sums for 6, 5, and 3, the answer for 8 automatically is known. It is the sum of those answers. So that's what we need to do. Now the tabulation approach is basically similar. For tabulation, we basically need to know that in what order we should find the answers to the problems or subproblems. So in this case, if we know the answers of the smaller ones first, we can calculate the bigger ones. If we don't know the answers for the smaller values of x, we can't calculate for the bigger x. So the order is known. The order is smaller to bigger. First, we need the answer to the smaller subproblems, smaller values of x. From there, we can get the answer to bigger values of x. So this is our DP array. We know that for 0 there is only one way, do nothing. So that way it is there is only one way. The others can be filled from here. We can basically say that for 1 we need to take either 2, 3, or 5. There is no such way. We cannot take anything because 1 is less than all of 2, 3, 5. So there is no way. For 2 we can take 2, and thus we get our sum from here. For 3 we can take either 2 or 3 as our last step. If we take 2, there are 0 ways. If we take 3, there is one way. So 1 plus 0 gives us 1. Now, if we have to get 4 again, 2 and 3 are two possibilities for our last coin. So 4 minus 2 and 4 minus 3. We can look at this part of the array that we have filled, and from here we can fill it. 4 minus 2, that is this value, plus the previous value. We get this as summation. Similarly for 5, 5 minus 2, 5 minus 3. 5 minus 2 is 3, plus 5 minus 3 is 2. The summation gives us the answers, and 5 minus 5, that is 1. The answers to all of them give me this answer, that is 3. Similarly for 6, I can basically sum up 3, 4, and 1. That is 6 minus 5, 6 minus 3, 6 minus 2. I add them, I'll get 2. For 7, I can similarly go to 7 minus 2, 7 minus 3, and 7 minus 5, that is 2. If I add them up, I get 1, 1 plus 1 plus 3, that is 5. I get 5. And for 8, if I calculate, similarly I'll get 2, 3, and 8 minus 5, that is 3. This actually gives us 6. So we actually get 6. How much did we get above? We are getting here 2, 3. Yeah, we got 5 over here. Maybe we did something wrong. For 6, we have found 2 ways. For 5, okay, I missed that thing. For 5, you can take 5 itself. For 5 you can take 5 itself, you have 0, so you will return 1 from here. Yeah. So you have 3 over here. So basically you have 2 plus 3 plus 1, which is equal to 6. That is the answer for 8. That's how you get 8. I mean, for you get 6 for 8. And if you calculate for 9, you should get 8. Let us see. 9 minus 2, 9 minus 3, 9 minus 5, that is 4. So we get 1 plus 2 plus 5, that is 8. So this is the tabular way of doing it, which does not involve recursion call stack. We have discussed the differences between tabulation and memoization, the advantages and disadvantages in that common DP class. You can look at that video. I have shared in the description the common DP class video. So in that way you can basically implement. In this case, if you follow that logic, basically tabulation is in many ways better over here, because in memoization also we need to visit all the elements, and that involves recursion, slightly greater time complexity. Due to that, we are not able to do a lot of optimization using the recursion. Optimization in recursion happens when we need to visit only 50 out of 100 or 200 elements, but more or less we have to visit all the elements as we see over here. From 8 we have to visit all the elements like 0, 1, 2, 3, 4, 5, 6. Almost everything is visited. So there is no significant advantage of using memoization over here. Tabulation works better in this case. So now I'll show you how we coded the tabulation for the dice combinations thing, where we had to form a sum of n by throwing a dice each time 1 to 6. We basically said, hey, go from 1 to n. That is, from 1 to the particular sum you have to reach. So for each sum, keep on calculating. For each I basically refers to a sum. For each sum, calculate what you will get. In this way, we are moving from left to right. Here also, we are basically doing the same thing. For each I, let's say 3, we are finding it out from the sub-problems, and then we are moving to the next problem, that is 4. And eventually, we move to 9. So we are basically saying, hey, move from 0 to the last thing, that is a sum. So let's look over here. That's exactly what we did in the previous problem, that is dice combinations. And for each I, we basically said explore all the alternatives 1 to 6. Now here our alternatives are not 1 to some place. It's basically the array elements. So instead of going through these elements just like that 1 to 6, we should go through the array elements. So basically from AR0 to ARn-1 or something like that. And then we basically said, okay, if it's an invalid option, like you have to form a sum of you have to form a sum of I, and your option is greater than that, then we will not take that option. We will basically take the other options. Answer I plus equals to answer I minus j. So we are basically adding up our answers to the sub-problems. Same as we did over this. So for DP, this is the most important thing. For DP, we form the recurrence. That is what will be our DPI based on the smaller DP or the other sub-problems basically. It will be the summation of j belongs to 0 to n minus 1 such that the ARJ is less than equal to I. We basically say for all these j, add up the DP of I minus j. Sorry, I minus ARJ. Yeah. We are going to add them up. This is our recurrence relation. So in the above case, DPI was equal to DPI minus 2 plus DPI minus 3 plus DPI minus 5. So the same thing, if we generalize, this is how it will look like. For each array element which is less than equal to I, do this. So that's it. If we get back, this is how the coding solution will look like. See, it starts in the same way. Answer of 0 equals to 1, that is the base case. We did something similar over there. Answer of 0 equals to 1. This is your DP array, answer array. And then I basically said go from 1 to x. So basically the target, start with smaller targets, go up to the largest target, and for each I, explore the possibilities. So you go through the n array elements, and for each array element take that in val, and if that val is less than or equal to I, same thing as over here. If this arj, is less than or equal to I, then that I minus that val is going to count. dp of I minus val, answer of I minus val is going to get added. At each step, please definitely do this to avoid the overflow, to ensure that your answer stays in int when you want it to stay in int. Otherwise, you can take in long also. In this case, I've taken in long, so not much worry. We can do it at the end as well. So yeah, at the end, this is the answer. Whether we can do at the end or not depends on how big the sum becomes. So it's always, almost always, it is better to do this modulus instantly. So that's it. This is how all the number of ways problems can be solved. Do try this problem yourself. Do try coding this problem yourself. Do try coding it using memoization as well. Even if it does not pass over here, that may be due to some time limit edges, but still it will be a good practice. And let me know if you have any doubts. Take care, keep coding, and see you all in my next videos. Thank you.